Hello, everyone, and welcome to our research project. Our topic is Web Service Discovery. I, Pranita Menavlikar, will be presenting this topic along with my teammates Bhavan Jethra, Chaitanya Patel, and Jenny Vyas. So, the overview for today's presentation is motivation behind choosing this particular topic, followed by introduction, literature review, implementation, future scope, and conclusion. So, what was the motivation behind choosing web service discovery? With the advent of size and velocity at which data is generated today through different applications, sensors, effective communication, be it inter applications or intra applications, is like the need of the hour. This has created a demand for services that can handle the computations which a consumer cannot. These services are available all over the internet. Real-time discovery of these services has become like the need of the hour. This is facilitated by web service discovery. And thus, this becomes an important topic to study for service-oriented computing. But what do you exactly mean by web service discovery? As the name suggests, is the process of finding a suitable existing service for a task. It facilitates service reusability and allows the end users to do more with less infrastructure. It has created like an industry for organizations and individuals who can offer efficient services according to the needs of the market. So let me tell you a brief history about web service discovery. So decades back, when communication used to happen, when there were no web services, it happened through ad hoc approaches, which used basic internet infrastructures, or through remote procedural calls, which are commonly known as RPCs. Then web services came into existence. So a web service framework comprises of communication protocols, which is usually SOAP or REST, then service descriptions, which are WSDL links, which we have been using throughout our assignments, projects, and service discovery. So before actual web services took place, UDDI was used for discovery. Then came into existence RESTful web services. So in currently, REST services are so popular because of their performance, because of their amazing performance and their lightweight nature. Despite REST, despite services being REST or SOAP, high latency is a major bottleneck in service discovery that needs to be addressed. For understanding web service discovery, we found out that web services can be described as semantic or non-semantic. Like they have semantic nature or non-semantic nature. Non-semantic web services are described using WSDLs and utilize details about service functionality, access protocols, and endpoints. While semantic nature uses web ontology languages, XML is used to construct the basic blocks of such web services, which are used for communication through XML protocols like SOAP or REST. So we study the semantic nature and non-semantic nature of web services in detail in our project. In our project, we are going to implement the non-semantic aspect of web services discovery using the GoDiscovery approach, which is seen in the second point. Then followed by that, we come to enhancing web service discovery for a distinct group of consumers. So this can be thought of something from the provider's side. It does happen that services keep changing, like some links become unavailable after few time, and many consumers are using these services. So updating each client for a provider is very difficult. So in this particular research paper, we found a very interesting approach. We found a very interesting approach where they are clustering consumers based on the use of their services. So for example, all travel users are being clustered together, all vehicle registrations are being clustered together, etc. And then we come to some optimizing techniques of web service discovery. So in this, a lot of indexing and caching methods have been described in depth. So today I will be particularly describing the first point, which is the semantic nature of web services. The proposed framework is a RESTful hypermedia driven framework, which is nothing but it uses REST and hyperlinks primarily in its architecture. This can be as simple as representing resources, which is the basic information which has to be communicated using hyperlinks to other related resources. So if you want to access X resource, then probably your X resource is being fetched through Y, Z, and A, B, C resources. The JAX RS specification used here provides group of APIs to develop REST web services by exposing Java classes as resources. I will be showing you a screenshot later, which uh, which which will give you an idea of how these classes are being exposed. The main goal here is to offer clearer semantic meaning of RESTful web APIs, which is ubiquitous all over the internet today. So how have they managed how have they achieved this particular framework? For the semantic representation, they are using four main annotations: path, entry point, semantic collection, and vocabulary. Path is the JAX RS annotation. Entry point is nothing but the starting representation of the web API. Semantic collection is the collection of resources identified using URI in the ID attribute, URI as in the uniform resource locator, uh, while vocabulary defines the URI vocabulary of the resources and its related resources as well. So in this particular screenshot, you can see that this is one class which is being exposed, and this is another class which is being exposed. So probably this is the client class which is being exposed. The client is requesting, is giving these particular details, the given name, surname, reward, image, selecting these particular things. And this is being sent to the server side. The server side has its own functions written in its class, and this is being given by the server. So in our project, so this is the semantic nature of web services. But as I said before, that we are going to experiment with the non-semantic nature in our project. So Bhavin will explain the further non-semantic aspect of it.
Hello everyone, I am Bhavin Jetra and I am going to continue talking about the research paper that I had taken up during this project, which is an implementation of GoDiscovery. So to talk about the gist of this paper, it is exploring the non-semantic nature of web services discovery. So as Pranita just talked about the semantic way of how the web services are being discovered, it concludes that the high-level matchmaking is done through those aspects. But since the advent of natural language processing and other fields, the non-semantic nature became more prevalent as it uses information retrieval and these techniques which are being advanced right now in the field. So as even in the field of web services discovery through non-semantic way, there are ways that can be done using brute force. So it is a very accurate way of doing the web service discovery. However, as we could just guess, it is more time consuming compared to the other methods. And hence, there were more further research done, and there was a Google web service, so a Google search engine built that was taking the concept of natural language processing methods to a next level, where it uses TF-IDF matrices and KD tree that helps in finding the web service discovery in a quicker way. However, the problem with that was it doesn't have a standard naming convention. So it is very binding that you need to know exact parameter names while doing the web service discovery. Hence, it is not recommended. Therefore, the researchers of this paper came up with a newer approach that was named as GoDiscovery, and it is a lightweight, more efficient, quicker way of discovering the web services. So the main crux of this method is making use of the TF-IDF metrics and the KD trees for accurate, efficient, and faster retrieval. So let's get more into the details of these things. So first of all, what is TF-IDF? TF-IDF is a very newly advanced statistical method in natural language processing that is taking care of, that is making use of the existing corpus, the documents in the corpus, and finding out what are the most prevalent words having high importance in the whole corpus. So essentially, it is just extracting the importance of a word, and it's a statistical measure that is used to estimate the importance of word in a document and or in a collection of documents too. And the words with a high TF-IDF score are often the words that will be describing the topic of the document also. So these are very prevalently used in text mining applications. So just to break down the TF-IDF, so it stands for term frequency and inverse document frequency. So TF is calculating the frequency of a word in a document, while the IDF encompasses the whole document. So as for the corpus, it will get the importance of the word across the corpus. And the way the importance is calculated is by taking the log function on the calculations being done for this value. Now, breaking down the GoDiscovery method. So as we said, it takes TF-IDF to match the user queries against those components. And then once the TF-IDF is generated, it creates the KD trees based on those so that the user has quicker access to the search results. And then when the user is querying for a service discovery, it will traverse the whole KD tree to fetch the matching services. So let's see the architecture of the proposed approach, which is, if you see on the top left, it is the list of WSDL documents that were being used. So it technically targets for the SOAP-based WSDL documents, which will have a SOAP message header that contains all the different tags, like the message input parameters, operation names, port types, and the service names, and the description tags as well. So a list of whole documents is present, which goes into the word extraction. So the content word extraction is doing the pre-processing of the files. It will calculate, it will pre-process and remove the stop words and do the stemming on the words. So these are some natural language processing based techniques in order to remove unnecessary words, like the ones which are very highly dominant. Suppose the word WSDL is primarily associated with most of the services, so you don't need it to be retrieved in every time. So you remove those words so that only essential part is remaining. So once the pre-processing is done, it creates a vector of all the remaining words, and then you pass on that matrix, you build the TF-IDF model. So the TF-IDF model will be a key value pair which contains the word and its occurrence in the whole corpus. And once that TF-IDF model is built, it will be passed. It will be used to generate. It will be used to generate the KD tree. So the KD tree will be built on this matrix, which will be used for getting the search results when the user puts in a search query. And on the bottom half, here's the second part of retrieval. So a user will submit a user query, which will again be passed through the pre-processing step, and it will be converted to a TF-IDF vector, and that vector will be passed to the KD tree to find which vector does it closely resemble to. And then the response would be given based on the number of web services that were matched. So in order to go through the whole process again, the algorithms which were built for this are listed here. So build index algorithm is the one in which it takes all the WSDL files and then it extracts the words. It will remove the stop words. It will do the stemming and create a bag of words. And then once we have that whole bag of words, it will generate the TF-IDF model. And then that model will be sent to the build tree. So that will generate the KD tree. And then the algorithm 2 is for submitting the query. So a user, when they want to search for a specific service, they will send the query, and again, it will go through the same process of stop word removal, stemming, and then creating a TF-IDF vector. And then that vector will be passed to the KD tree find function. And then the KD find function here, it will retrieve the n most resemblance or relevant services. So it's a recursive function. It will traverse the tree. It will keep on going into the depth of the tree until it reaches the leaf node. And once it reaches there, it will give all the nearest neighbor services that were stored in the leaf node. So based on this approach, since the generation of the TF-IDF matrix and the KD tree is done on the go, it is always online and it's being updated in the background. So the user doesn't have to wait for generating the TF-IDF matrix and the KD tree all the time. It's a quick process because KD trees are quite prominently fast. So when comparing the accuracy, the precision of the model was quite high. If you see the top two precision shows that the two prevalent services were almost always accurate up to 10. And then when 20 or 15 services were listed, that time the list was a little off, but that's something that is not very much in demand. If you get 10 accurate discovery results, that's good enough. And then when comparing with the other baseline models, the brute force is definitely more accurate than the GoDiscovery because brute force is exhaustive and it covers a whole list. But the downside was it takes a long time. But just to ensure that the GoDiscovery is not way behind, we found that it is still about 91 and 92, so it's not a very huge difference accuracy wise. So the advantage of using GoDiscovery and where it beats the other models is with the time processing. So that's the selling point of this model. So if you see the time taken for 25%, which is about 927 services, it takes about 2 seconds to build the TF-IDF model and again to generate the KD tree. So which is quite fast and it is comparatively way efficient than the other models that were being used. So that was it about this paper, and then we would have the next participant showing the research work done in their paper. So thank you so much.
Hi everyone, I'm Janil Vyas and I'm going to talk about the paper which discusses about the enhancing web service discovery for distinct group of consumers using usage profile. So this paper presents a framework called Service Evaluation Framework, which is used to develop a KDD, which is knowledge-driven data discovery process, which uses monitoring of client requests to keep the database updated based on the recent requests from clients. The output of this process is a set of useful service usage profiles just from a set of interaction logs. This KDD process can be developed based on time, or spatial parameters. That is, the client can either use parameters like request in last 1 month or 3 months to store the request in the database, or use regional mapping of requests to store the request like request in NYC or San Jose. Moving on to the three main components. So the first one is logging and monitoring of client requests. Here it is like assume that the messages are exchanged in the SOAP format. The HTTP layer is used to intercept the service interaction because the web servers record the HTTP request in server logs. Second step is storing the data. That is all the log files in a user's database. The user's database is a general purpose centralized repository that contains detailed data about service usage, which can be used to perform different analysis. Extraction process is performed on all the new raw log files to get all features used by each client application. That is the service version, the operation requested, and the parameters exchange. The third and the most important step is applying this KDD process to drive usage profiles. KDD is a bit complex process, and to hide this natural complexity of a KDD process to the user of this framework, the discovery of profiles is developed by parameterizing a set of predefined tasks. So there are 4 different tasks which the user has to interact with. The first is provide parameters to select data from the user's database that meets the analysis goals. Selects among predefined data transformation alternatives. Parameters. Third is parameterize cluster algorithms and compare the results using matrices. And the last is triggers the automatic generation of profiles for validated clusters. So the authors of the paper of this paper have used synthetic data to simulate request to a real service. To create this database, the eBay trading service is used with 7 common workflows. Like an example of the workflow is get taken workflow, which has 3 steps. That is get session ID, fetch token, and get eBay official time. Another example of a workflow can be buy item workflow. So the 3 steps are place offer, add member message, and leave feedback. The data consists of 525 applications distributed in 6 profiles, which perform 448703 requests for 42 operations. An example of the profile mentioned above is like a buyer profile, which has a 5% probability of going through a get token workflow discussed above, and a 95% probability of going through a buy item workflow. JMeter is a tool they have used to generate the request to these operations. So moving on to the 4 algorithms they have used to perform the to compute the user profile. The first one is a k-means. So that is basically a partitional centroid based algorithm. Second is hierarchical agglomerative clustering, which is a hierarchical and a well separated. And third is dbScan, which is partitional and density based algorithm. And the last is expectation maximization, which is a partitional and distribution based algorithm. So as you can see, all the 4 different custom algorithms belong to different classes. So the different criteria used for evaluations are basically the distinct profiles represented by clusters, pair counting F measures, and the number of generated clusters. The results are, the first result is the most effective algorithm for this user's profile discovery is hierarchical clustering using mean linkage, which perform better for both binary and weighted data. So the binary is basically if there is a data which distinguishes just on the basis of whether the operation is done or not, so that it's like 1 or 0 for the operation. The weighted data is basically a different set of operations with a different frequency of occurrence. The other is the k-means and the EM algorithms could not distinguish profiles that differ only in the usage frequencies, clustering together P6 and P8 application, which has the same set of operation but with a different frequencies. They could also not detect subset relationship like the k-means merge profile P1 and P2 in a single cluster, and EM merge P2 and P2.2 in the same cluster. So the future improvements that are suggested for this to improve the efficiency of this framework is using unsupervised clustering assessments, more data, better cost estimation, and mechanism for exploring and interpreting the profiles. So, and another, you can see that it's basically implemented for a SOAP-based services, or that all the raw log files are for only the SOAP-based services. So it can further be improved to integrate the saving and the data exploration for the REST APIs.
Moving on to the optimizing web service discovery part. Service discovery can be considered as a web service in itself, which receives requests about the required specifications and it returns the result as a list of web services which can complete the required task under the requested specifications. We saw different ways of searching for the right web service. One more way of optimizing the search would be to introduce a cache for web service discovery results to reduce the load on the backend discovery system. Caching has already been proved by research to be able to improve the web service performance significantly. Caching popular objects on the client side has been recognized as one of the most effective solutions to reduce web server bottlenecks, reducing the traffic over the internet, and improving the scalability of the overall system. In the case of web service discovery, caching not only reduces the user perceived delays, but also reduces the computational load and network bandwidth usage of the backend service discovery engine. Traditionally, caching mechanisms focus on choosing an optimal eviction strategy to remove the entries which have not been used often. Hence, the aspect of caching usually studied is how to decide which item to remove when the cache becomes full. It assumes a limited cache size which we have to use sparingly. This paper looks at the problem in a whole new way and proposes an altogether different approach to caching. So due to the abundance of data storage systems nowadays, this approach wants to take use of that and not use a limited size. So this approach assumes unlimited cache size, like an infinite size to store all the results, and a limited cache refresh rate. So instead of deciding which records to remove from the data, this approach focuses on deciding the refresh rate to frequently update the records in the cache. So here the bottleneck is the cache refresh frequency rather than the cache size. So the essential function of the proposed approach is to keep on refreshing cached objects like a weighted periodic scheduling problem. The paper proves a fundamental upper bound on the expected number of cache hits, that is, the number of times a refreshed record was requested, that can be achieved by any refresh strategy. The proof corresponds to the optimal solution of a fractional knapsack problem. The bound is the maximum gain of the chosen algorithm. It is an NP-hard scheduling problem, so the authors used heuristics for the proof of the proposed theorem. The task is to keep a cache of service discovery results up to date under a restricted refresh rate. The paper evaluates a number of algorithms with an experimental study. They are as follows: greedy algorithm, power of 2, random LB, past penalty, earliest deadline first, tree max, and tree av. The authors evaluate the performance of these cache algorithms mentioned by using randomly generated problem instances which represent a broad range of different situations. Power of 2 EDF and past penalty performed well in these experiments. The power of 2 algorithm provides the best cache performance of more than 95% of the theoretical upper bound in all scenarios. The EDF method has a comparable or even better performance in all scenarios. Its gain is less predictable, but as it is within 90% of the optimal solution on nearly tested instances, this might not be a drawback in practice. The evaluations in this work are based on the assumption of specific distributions of job periods and access popularity. Now we move on to the implementation part, which Bhavin and Jenil will present.
I will be talking about the implementation part for our project now. So our implementation is almost similar to what they've implemented in the GoDiscovery paper. So for this particular implementation, we have a set of around 15,000 files, WSDL files, and we have extracted data from the following tags like service name, port type, operation name, message input, and message output. So by saying extracting the data, what I mean is we are extracting only the meaningful keywords by removing all the stop words. So we have removed all the duplicate keywords as well. So we only have a set of unique keywords. It can be a normal word, action verb, or noun. And they're all inside the database in a column called WSDL description. So about the data. So we have used the data from research from a university. So the particular data was extracted from the web crawler by using the WSDL links from the CSV file we received from this particular research project. So we have used Zeep to parse all the WSDL links to fetch all the WSDL files. So after fetching all the WSDL file, what we have implemented a function which goes through all the complete different WSDL data files and extract all these meaningful keywords. This is like the fun phase of our project. So this is basically where you enter all the keywords you want to search for the particular API. And this is an example of a output of all the web APIs you get as output for the particular keyword called vehicle. So there is basically two stages in our project. The first one is, and we have implemented it using two different Python files. The first one is generating a TF-IDF matrix and the KD tree from all the keywords of the WSDL description. So right now our implementation is like whenever a user passes a query for a keyword, we generate a KD tree and a TF-IDF matrix again and again for every single query, because saving both of them and updating it every time a new service comes up, so it takes different storage structure and all the stuff. So right now we are just preferred making it dynamically. So the first step is making a model of a KD tree from all the already existing WSDL keywords. And then whenever a user passes set of keywords. So, and again, that is actually a new query. So query is transformed into a TF-IDF matrix and then passed to a KD tree. So KD tree we have implemented is we have used sklearn library and used the KD tree feature of the library, and it has a function called query radius. So what we have we have thought of doing is like after passing the TF-IDF matrix of the query, which is basically a set of keywords converted into a TF-IDF matrix. So we are passing as one of the parameters for the query radius function, and the other parameter is specifying a radius. So right now, after like we have performed like 40 of the testing, different 40 testing scenarios for a different set of keywords. So for each of them, we have found out like putting the distances cutoff right as 1.4 gives a very good result. Like all the retrieved APIs are more related to the keywords. So how this function works, the query radius is like out of all the related APIs that could be possibly related to the keyword that we have passed, it it chooses only the ones which have a radius less than 1.1. That is a distance from the actual query of all the nearby existing API should be less than 1.1. So the result is like we have used a subset of all the WSDL file, which basically was 15,300, and we have just used 750 for now. And we have used the radial distance for the query radius function, that is 1.1. And iterations we have used is 40. And out of all the 40 different searches we have done, we have like gotten 100% accurate result for only 34 of them. So that gives a F1 score of 84.43, and all the performance of all the 40 result was done in 2 seconds. For the future code, we thought of using a bitmap index and a hash indexes for a better traversal, but it again requires a lot of research. That is it feasible for the implementation? Is it feasible to store all this new structure? So there are some services which does not have a specific related keywords. So what we thought of, like if a user enters a set of keywords to be searched, we could present to him a set of more related keywords which are actually present in the WSDL file for him to choose from, so that he can get a more relevant set of resulting APIs. So the conclusion is studying discovery techniques, we successfully implemented a web service system making the most of the non-semantic nature of web service, like using TF-IDF matrix and KD trees. So which is kind of a clustering algorithm on the web service component, which can be used for discovering REST or SOAP web services. Since we have implemented it for the SOAP services, but as we like going through the implementation, we saw that we are actually like passing all the WSDL files. So we can also pass the REST API file as well to get all the important keywords. So the implementation is more of on a general basis. So right now, since we only have a database for all the WSDL files, so it is more aligned to the SOAP web services. But then it can be modified to integrate the REST APIs as well. And it can be further improved. Like for now, we have just removed the step words, so, but we can in future we can use some natural languages, language processing, machine learning, which has some promising results in service-oriented computing as well. Like we can use stemmatization, lemmatization, all this to shorten a particular verb, like cycling, to not just shorting down the cycling word to just a cycle, and all, like just to stem down to the root word. So it improves the matching and the accuracy of the resulting APIs that the user is searching for. Thank you.
So these are our references. From these, 3, 5, 9, and 10 are our main 4 papers. The other papers we have referred here are for mainly used for understanding TF-IDF, KD trees, semantic and non-semantic nature of web services. And basically, these have helped us in our code implementation. Thank you. Hope you stay positive and keep testing negative.